Welcome to the Montana Instruments presentation on sample mounting. This is specifically intended for material science researchers operating at temperatures below 10 K. Most of this material will be in the context of an optical cryostat, which requires optical ports and temperatures in the single-digit Kelvin range. We'll cover the basics of thermal transfer, how to mount your sample, sources of losses, including wiring, and radiation heat transfer through the windows. We'll talk about some standard ways of analyzing the magnitude of your losses and ways to connect to a sample that is being moved. Let's begin with some heat transfer principles. Heat is exchanged between objects by radiation, convection, or conduction. Radiation is a major concern in any optical system, yet is often overlooked. Radiation varies as T to the fourth. It can be kept small, but mistakes here can allow heat to creep in and add a significant heat to your sample. Convection is actually a special form of conduction and for the most part is a minor issue in a vacuum system. Conduction is the primary way in which heat flows in our systems. We'll explore that in detail. There are two primary modes in which heat is transferred in a material. These are electron travel and lattice vibrations. For electrically conductive material, heat is transferred primarily by electron travel. Lattice vibrations are more dominant at room temperature or in electrically insulated materials. In fact, at Montana Instruments, when we test new materials, we often just test the electrical properties at low temperatures because that's a very good measure of what the thermal properties will be. Here is the Fourier heat transfer equation. If we move the temperature gradient over to the other side, we've got heat, Q, which is the heat flow in watts, over the temperature difference. And on the other side of the equation, we have A and L, which are the geometric constraints, and K, which is the thermal conductivity of the material. Let's also make T2 minus T1 to be 1 Kelvin. That's helpful in doing calculations. We come up with the term conductance. This is a great way to look at parts of a system to see how well you are transferring heat. So watts per Kelvin, meaning conductance, is basically a measure of the effectiveness of transferring heat. This is important because you can look at a thermal link, a sample mount, a certain interface, or a series of interfaces to estimate performance. You can look at a specific component or a number of components linked together. When we're looking at a new design or a new geometry, the isolated details are not important. Let's just look at the conductance because that's all that really matters. As an example, a typical interface has a conductance of 1 watt per Kelvin. This is a good number to shoot for. Some parts of the system will have a conductance that is higher or lower than that. In this case, you've got an active load of 10 milliwatts from your laser. You would expect that your temperature would rise by 10 millikelvin. We just saw that heat flow depends on the conductivity of the material, the cross-sectional area, the path length, and the temperature gradient. Here is a connection between two parts. You are probably familiar with the principles behind this. The materials need to be conductive. It helps to have a large area, smooth surfaces between the areas, and then a soft surface, gold or indium for example. Gold is a good interface. Bare copper will oxidize. Even if you have nice, polished, clean copper, it will immediately grow an oxide layer. So if you put two copper pieces together, you get an oxide layer in between, and this adds to the boundary resistance. Now, if you have copper parts that are coated in gold, then you don't have this problem. If Master Yoda was here, he would say, if you have force, use it. It turns out, if you have force, you don't really need area. This becomes very useful in cryogenic engineering and also in sample mounting, especially if you're doing something a little bit unique in the sample area. Most of our customers are doing just that. The best way here is to have conductive materials, smooth surfaces, a soft gold plating, and a bolted connection, which adds force. A good rule of thumb is that a good bolted connection is worth about 10 watts per Kelvin. That's the conductance for each bolt. Let's put this into perspective. Consider these large surfaces here. Let's put a bolt here, 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 and here. If we add that up, that's 40 watts per Kelvin. That's an enormous conductance due to a very high force area in each one of these locations. Note that the surface area is really not buying you much because all the conduction, 10 watts per Kelvin, is happening at the very localized high pressure areas. This is an example of why you don't need large surface areas if you have force. Often, it's not feasible to have a lot of surface area because the sample mounting space is geometrically constrained and there's a lot going on. What really goes on at a boundary? If you look closely at any boundary, it will just be a series of peaks and valleys, and you've got a potential problem. Notice there are really only one or two peaks really touching here. Everything else really doesn't contribute to the heat transfer between these two materials. Let's see what happens when we put some thermal grease in there. Now we've got grease for conduction across that interface, but as we know, grease is not a great conductor. You really haven't added much conductance to this joint. If we smooth down those surfaces, we still have only one or 2 points contacting, but we do have a smaller interface for heat to travel through the grease, therefore the conduction will increase. The best way to do this is to have smooth, greased surfaces that are also pressed. Now you see the points of contacts are much larger and the surface area at each one of those contacts increases the force. You also have a smaller interface for the grease and a smaller distance for the heat to transfer through the grease. Let's look at the relative conductivity of various materials. As you would expect, most metals do great, except stainless steel, which is in a class all by itself. Copper can vary a lot, but even if you get high purity material, once it's worked or machined, then the performance drops back down. Also note that vacuum grease and GE varnish, commonly used in vacuum applications, are unfortunately poor conductors. They can be used to increase conductance if kept thin. Montana Instruments makes a material that has a very high conductivity. This is partly based on the material and partly on the geometric shape of the part. This is part of our patented process here at Montana Instruments. Let's talk about how to understand the magnitude of losses empirically. If we can measure how well we're doing, and then we can measure improvements, this can help us home in on what changes work and what don't. Let's start with a black box approach. Heat goes into your sample from the several sources shown. Heat goes out through the cold finger in this case. Rather than model each path imperfectly, we model the system response to power input. This gives us the thermal absorption rate of the system measured in degrees per watt. You can also think of this as the slope of the system power curve. This is dependent on the entire system status, including the temperature, windows, wiring, and other things. Once we know this, we can try improving sections of that system and see how much they contribute to the losses. Here is a power curve which represents the system base temperature for a certain amount of input power. By knowing where we are on the curve and what modifications we make to the system, like wire attachments or input laser power, we can estimate the operating temperature under our experimental load conditions. An easy way to measure the status of the system is to input a known amount of heat and measure the temperature response. Once we know the system temperature rise in response to a watt of power, we know where we are on the power curve for the system. We can calculate, for example, if we put 50 milliwatts into an RF cable, what the temperature response will be. Or if we add another 36 gauge wire, what the base temperature will change to. Similarly, it can help us identify problems. If we calculate all the loads of the system to be much less than this value, we can start to track down where the problem might be. For example, a wire in the cold space that unexpectedly touches a shield at a higher temperature will result in a heat loss. One of the myths we want to dispel is that a bigger cryostat will solve all your problems. If you need more cooling in a wet or liquid helium system, you can just open up your valve and get more cooling. That's not the case with cryocoolers. Engineers in that environment can allow heat loads much higher than needed. It's natural to say that just getting a bigger cryocooler will solve your problem. That may not be the answer, and that may not even help, as we'll see here. Let's start with the sample. We'll put a radiation shield around it. This protects the sample from the radiation of the warm surfaces all around. Let's put a vacuum housing on it so we can pull a vacuum. It's an optical cryostat, so let's put some windows on it. Notice the radiation shield doesn't have any windows, but rather openings. This is what most instrument manufacturers do, but it's not the way we design our instruments. As a result, we have radiation from the warm surfaces, the windows, directly onto the sample. In this diagram, we aren't showing the radiation that comes through the vacuum windows and hits the shield. As a rule of thumb, assume about 50 milliwatts per open window based on a 1-inch window. Actual values could be anywhere from 20 to 100 milliwatts per window. So for 3 windows, the total is 150 milliwatts, shown on the log scale. Let's put some positioners in the sample space for XYZ motion. Positioners with feedback require 5 wires per stage for a total of 15 electrical connections. Let's use copper wire in this example because that's what's commonly done in the field. We'll thermally lag the wires at the radiation shield, which is good practice. We might see 150 milliwatts at the sample depending on how well the wires are lagged at the radiation stage. The heat load goes up from those wires as shown in the graph on the right. Let's also put some RF connections in there as well. You might add 100 milliwatts for 2 coax RF cables. We've accumulated a significant heat load. Now let's try to do things a little better to reduce the heat load. We still have the radiation shield in place and all the electrical and RF connections. First, let's add some windows. We had 50 milliwatts per window. These new windows are thermally attached to the radiation shield, so they don't need to hold a vacuum, but they block most of the radiation coming through and only pass the visible portion of the spectrum. You might see 1 milliwatt per window. Now, instead of copper wires, we switch to phosphor bronze wires. Copper may be easy, but it's not the best. Your heat load may drop to 8 milliwatts. The actual might even be lower. You can drop this further by adding some length between where the wire is lagged and the cold stage. Now let's replace the coax with microcoax designed for thermal resistance. Again, this is a conservative measurement. So now in this example, we've reduced our heat load to about 20 milliwatts, and we've got the same functionality we had before at 400 milliwatts. This leads us to part 2 of the I think I need more muscle section. When we look at the sample in the center, it's heated by the sources we saw, plus your experimental inputs. Most samples have high emissivity and act like a black body absorber for all the radiation present. Let's add a laser through the sample in the center. Notice we have opened up the top radiation window, which you may need to do for low working distance application. If local heating is the problem, then sizing up the cryocooler is not the answer. You may have a heat load of 100 or 300 milliwatts. If that heat load is local to the sample, then your sample temperature may go up many degrees. Your sample may be at 15 K, and sizing up a bigger cryocooler will not help that problem. A larger cooler might get you a marginal improvement to 14 K. The problem is the temperature depends on the quality of the sample thermal mount to the cold finger. You need to minimize the heat input and optimize the sample mount connection. Hopefully the series can help you do just that. Now let's talk about bonding, both bonding of wires and bonding of samples. The purpose of bonding is to physically and thermally attach an item to a surface. The idea is to maximize heat flow from your samples and wire attachments to the cold surfaces of the cryostat. Thermally connect your sample to the coldest part of the cryostat and then keep any attachments like wires as cold as possible by thermally lagging or connecting them to other cold surfaces. Typically we lag wires to the radiation shield at about 30 K because that stage can extract a large amount of heat, and then the only thermal path is from 30 K to 3 K at the sample. Let's talk about wires first. Here are 2 examples of a wire being lagged to a surface. We often use VGE, also called GE varnish 5031. It is solid at room temperature and can be removed with acetone. You get a small tube with a cryostation for mounting your samples and wires. What is important here is that the wire touches the surface. Let's look at why. You've got both Joule heating from current passing through the wires and conductive heating from the room temperature heat passing along the length of the wire. So you have 2 sources of heating through the copper that you need to dump to the cold shield. VGE has an emissivity of 1, so it acts like a black body absorber. Any radiation that is present is absorbed by the VGE and will end up as additional heat in the wire. Use the VGE as an adhesive, not to coat the wires. See this little space at the bottom? This creates a huge thermal resistance. This becomes very important as the heat load on the wire goes up from both the Joule heating and the radiation. So you can see on the right why it's better to have the wire actually touching the surface. If you can apply a force to the wire, you will do even better. Let's move on to samples. We often use VGE or N grease under the sample. Indium works well, especially if it's heated. The image shows two samples bonded. It's obvious that you don't want to mount your sample at an angle, but this happens commonly in practice because you can't really tell if your sample is flat on the surface. VGE is nice because it sets up very quickly, but this is the same property that causes trouble. You may just start to get the sample pressed down and the adhesive sets up as a wedge and the thermal conduction isn't very good. It's much better to use some force to help connect the parts better before the VGE sets up. Here's one trick that may be useful. Put a drop of acetone on the surface of the part. Then as you add VGE, the acetone thins it immediately. So you have a little more time to position the part before it sets up. And also the layer will be a little bit thinner. What we often do here is put a small weight on the sample until it sets up. It may be tempting to use a finger or a pair of tweezers, but as you're trying to apply force and while you're waiting a few seconds, the sample is moving around, and those small movements cause the bond and the small interface to be compromised. Here are some materials for sample bonding. Thermal grease or a Pison-An grease is pliable at room temp, but freezes at low temps. VGE is great for sample bonding. VGE is not permanent. You can add some acetone after your experiment and the bond will loosen up. You can add a little heat, say from a halogen lamp or a heat gun, but be careful with the heat gun because you can easily overheat your sample. If you can add a little bit of heat, then the setup time is quicker and within 30 minutes you can cool down. Otherwise, you should wait for 12 to 24 hours. One trick for holding items in place while your bond sets is to use unwaxed dental floss. We use this to hold things in place even if you are not using a bonding adhesive. The unwaxed dental floss is strong and easy to tie or cut to remove, but it is safe inside a high vacuum. Don't use the waxed or flavored varieties though. A good vacuum epoxy is another option if you can make permanent connections. Indium is another good choice. The problem is that it tends to be a bit thick and you've got to be aware of cold flow. So if you've got a bolted joint or some pressure on the joint and you've got indium in the joint, then if you cool down, the joint will increase in force and the indium will flow because it is actually soft compared to the joint and materials holding the joint. Then when you warm up, the indium can leave a little gap or have reduced force. Then the next time you cool down, you won't have as good of a conductance. In that case, just retighten the bolts. Let's talk about outgassing. It's important to be careful what you put in the cold space. Many laboratory materials have volatiles that will be pulled out of the material in a vacuum. There are several lists of materials which are acceptable for cryo work. Here is one example at the bottom of the page. One of the mistakes we often see is using rubber or Buta-N O-rings. They're soft and flexible, but in an optical application, on evacuation of the sample space, there are volatiles in the Buta-N that tend to evaporate and fly away. Some are pulled away by the vacuum pump, but many are not, and these molecules end up on a cold surface, like on the sample itself or your cold windows. You'll get contamination on your sample or end up with fogging on your windows, and these are very hard to remove. There are many types of wire that can be used in a cryostat. Copper is usually not the best choice. Phosphor bronze is fantastic for wiring piezos and heaters. It has a slightly higher electrical resistance, but a much higher thermal resistance. Manganese wire is also very good. It is more resistive thermally and electrically than phosphor bronze wire. Because it is more resistive than the other wires, you have to be careful not to use it on higher power applications. That's because the wire itself becomes a heater. In fact, this wire is great for making a heater in your system. We use this for thermometry and lower power applications. Beware that manganese wire is difficult to solder to properly. Wire gauge is also important. Smaller diameter wires have a higher impedance electrically and thermally. We often use 32 to 40 gauge wires, although the thinner wires can be very fragile. Beware of insulation on the wire. Most of the small diameter wire has a thin varnish coating which can be nicked and cause shorts. As always, take care with assemblies in your cryo environment. Let's look at a practical example of a wiring harness to a piezo. This is phosphor bronze wire with 4 twisted conductors. On the left, the cable will be plugged in the vacuum at room temperature. The connector on the right goes to the piezo. We will have about 17 centimeters of wire to a position where the cable will be thermally lagged to the radiation shield at 30 K. This results in a heat flow that can easily be handled by the first stage of the cryocooler. Then another 17 centimeters is coiled to make the cabling easier to manage in the cold space and finally connected to the 4K stage. This too provides a thermal distance that minimizes the heat flow to the lowest temperatures. A cable assembly like this, properly done, will only raise the temperature of the stage about 10 millikelvin. Researchers should have a good understanding of emissivity to manage heat losses in their system. Emissivity is a measure of the ability of a surface to radiate energy. Here is a table of values for common materials. Note that glass is 0.93. When doing calculations, we use 1 to be conservative. Most samples are somewhere in this range, very close to 1. Notice as a point of comparison, copper is 0.02 if it is polished and bright. This is not the case if the surface is oxidized or has oil, for example vacuum grease or finger oil on it. You can easily raise the emissivity of a part if you are handling it without gloves. You will leave a buildup of oil on all those parts and the emissivity goes up as well as the heat load in the cryo. And to make matters worse, finger oils will fly away when you pull a vacuum and you'll end up with these depositing on some cold surface. It is very important to maintain cleanliness inside the cryo environment. Wear latex gloves when handling the cold parts and watch where you set parts down on the table to avoid picking up surface contaminations. If your sample is on a moving stage, you must have a mechanism to pull heat from your sample without disturbing the motion. Braids are one choice. They're easy to buy and attach and can be useful in some cases. You should be aware of a couple things with braids. Braids are usually pure copper, which is always oxidizing. The more you handle it with your fingers, the more it will oxidize over time. If you look through a microscope at a small wire that makes up a braid, you will notice its surface is not smooth. In fact, it looks more like Velcro than a smooth surface. That's important when you're talking about vibration isolation. It's important that you have a very flexible material. If every one of those wires has a surface like Velcro and the oxide grows over time, then you'll have an interface at the surface that actually adds to the stiffness. Although this technique is commonly used, it may not work as well as you want for a high-performance application, and you may see degraded performance over time until it needs to be replaced. Wires and straps are good for vibration isolation and flexible heat connections. Ideally, you want a long wire to avoid transferring vibrations and a short wire to better conduct heat out of your sample. Montana Instruments uses a high conductivity material that is 15 times more conductive than the best copper. With this, we can have thin connections that still conduct heat efficiently. Gas may also be used to exchange heat. This may be required for hard-to-mount materials where the gas can provide complete contact and extract heat from your sample. Gas is great for vibration isolation. It doesn't transfer force through to the sample. However, gas is not a good thermal link. If, for example, the heat load in your sample goes up, then it creates a temperature gradient across the gas because the gas can't extract the heat fast enough. Your sample temperature goes up, and it doesn't matter how big your cryocooler is. Keep these things in mind as you design these connections.